So here's our last lab deflection, and we're going to look at the deflection of a little wooden piece of basswood here. You're all very familiar with basswood now. It's set up as a cantilever. It's actually 10.5 inches long, which comes from the fact that it's actually a foot long, and then 1.5 inches of it is held between this 2x4. And I've got it set up against this graph paper, and we're going to load it. Whoops, we're going to load it with these little weights. So here's the first one, and these weights, it's given in the data there exactly what they weigh. So we're going to put this on here and see what it deflects. And it looks like it's deflecting about, that's about 0.9, I'm going to say. 0.9. So one weight here gives it a deflection of about 0.9. And if I put the weight further back, as you'd expect, it deflects less. So the closer I get to the support, the less it deflects. So here at the halfway point, it's deflecting, about half as much. It's about 0.4. If I don't move the end of it there, yeah, it's about 0.4 actually. A little less than half, about 0.4. And then if I do both of them, I think that was the other part of the game. Oops, if it doesn't all tip over. If I do both of them, it should be the sum of that, if it doesn't hit the ground there. Okay, so what's that? That looks like 10, 11, 12 or so. It looks like about 1.2, we'll say. It's about 1.2. So the one you really have to calculate now, okay, would be this one on the end, and that is the one that we said is about 0.9. So what you're supposed to do now is the data is all given on the sheet here, and my little washers with the hook weighed about 0.035 pounds, and the moment of inertia on that for that 1/16 by half-inch piece is also given, and the E modulus of basswood is given, as well as the length. So when you calculate this, you put those numbers in there, you probably won't get exactly 0.9. You may get a little bit less. I didn't calculate it. Maybe a little bit less or more, but I'm sure it won't be 0.9 exactly. Maybe you'll be a tenth off, so maybe 0.8 or 1.0. And then you have to ask yourself, why isn't it exactly right? And of course, you can look at the input you were given and imagine what the degree of accuracy of some of this is. The length of 10.5, well, I can tell you that was pretty accurate. I think we got within, because I measured it on the stick, so I think we got within a few percent of that. So that was pretty accurate. The weight of my washer, I think that was an average for these washers and hooks. So that, and it's only 2 significant digits there. That may be maybe not quite so accurate. The moment of inertia is fairly accurate. I mean, that's for the dimensions given. I think that's the number you get. But the question is, how accurate are those dimensions? It's pretty accurate. I mean, those things are... I didn't take a micrometer and measure it, but with a ruler it looks right. The one you really have to ask yourself is the E modulus. I mean, that E modulus, I think I pulled off some website for basswood. And of course, there's a lot of variation, a lot of fluctuation in that E modulus for any wood. and how accurate that represents this specific piece of basswood, there's a good bit of potential error in that. That's probably the least accurate number in this calculation. And that's generally true when you calculate with wood. And actually the numbers that they'll give you in the code are very conservative. When you actually test wooden members, they generally have a little bit higher E modulus. And in fact, depending on how the E modulus is being used, if it's in buckling, which would be a critical failure based on the E modulus, column buckling, then they reduce it even more. There's an even lower number they give you, so it's, you know, trying to make sure that the wood you use would fall within that range. Okay, so that's the number I got, 0.9. You calculate and see what you get. You can do it with the using the graphs, and you can maybe also do it with the equations and see how close you get to 0.9. Good.